Hello there, and welcome to my YouTube channel. Now, I am a chemist and I specialize in organic chemistry, but over the next few weeks and months, I will be covering three important but yet undervalued and undertaught aspects of chemistry on an online platform. The first one is physical organic chemistry, written in short. Now, we know that physical chemistry involves things such as entropy and also Gibbs free energy, delta H minus T delta S. But how do we link that to an organic context? Well, some of you might have covered substitution reactions. So if I gave you these two substituents, bromoalkanes, and I hydrolyze them, we both know that they're going to form alcohols. The question is, well, first of all, we know that this is going to be a one-step SN2 mechanism, and this one is going to be a two-step SN1 mechanism. But if I was to ask you in the lab to prove this, you'd be thinking, well, how do I prove this? I know the theory behind an SN2, and I know the theory that governs an SN1 reaction, but how do I physically prove it in the lab? And that is when we're going to concern ourselves with entropy, some Gibbs free energy. We're also going to be linking it to reaction profiles. Not only are we going to concern ourselves with that aspect of physical chemistry with organic chemistry, we're also going to be talking about kinetic versus thermodynamic products. And also we're going to be discussing isotopic effects, which will also be linked to some spectroscopy and some application of zero-point energy. We're also going to have a whistle-stop tour of pKa and solvents. And then we're going to apply some of this knowledge at least, to general and specific acid base catalysis. We're also going to be covering MO diagrams. Now, MO diagrams are taught at the basic fundamental level, but they're not actually developed beyond a certain point. So we're going to be discussing how we build MO diagrams primarily for water, ammonia, the dimer of BH3, which is B2H6, and we're also going to then take it on towards octahedral systems. These kind of systems involve ML6 systems, a central metal ion, normally a transition metal surrounded by 6 different ligands. We're also going to be covering stereoelectronic effects. Now, pericyclic reactions are well covered actually on YouTube, but I do not particularly enjoy the learning route where 4n plus 2 or 4n electrons determine the product involved. I instead would cover Woodward-Hoffman rules without the need of learning any specific rule itself, and just look at the application on examples of organic processes. The final thing that I forgot to mention, which I'm going to cover in its own section as part of physical organic chemistry, is Ester hydrolysis. Of course, we know that there are acid and base hydrolysis, but there are different types actually of acid and base hydrolysis of an ester. If we look at this simple ester, which is methyl methanate, we can tell that there are two nucleophilic oxygens, and we can actually protonate or hydrolyze different parts of this ester, and it depends on which one we're going to hydrolyze regards to the conditions. So we have examples such as AAC1, AAC2, BAC1, and BAL2 are just some of the examples that we're going to be covering over the next few weeks and months. I hope you enjoy these few videos that I will be producing, and if you have any problems, please do feel free to drop it in the comments, and if you like the content that I am going to produce, please feel free to subscribe. And as always, I hope you have a fantastic day, and I'll see you soon.